Hello, now let's look at our AQA GCSE Combined Science Trilogy higher tier paper. So this is Chemistry 1 and this is 2024 paper. Now let's start having a go. Now for number 1 of this paper, it's about copper being a useful metal, and we're given this graph that gives us the production of copper between 1900s and 2010. If we're looking at this graph, we can see that this is the mass of copper produced each year in times 10 to the 9 kilograms, and we can see the year as it is passing by. Just a quick look at this graph, you can see that one conclusion we can make from that figure is the fact that the mass of copper produced have increased from 1900s to the 2010s. So that's something that we can note as one conclusion. Mass of copper produced increased from 1900s to 2010. So that's a conclusion that we can draw from this graph. Now, another conclusion that we can draw is the fact that the lowest production is in the 1900s. Right, so lowest production of copper is in the 1900s. And we can also draw that the highest, this is a third conclusion, highest production of copper is in 2010. And those are simple conclusions that we can make just by looking at a graph such as this. As we move on, it's about a mixture of copper and zinc. So we are heating to produce an alloy. So we're going to heat that to produce an alloy. So figure 2 shows the structure of pure copper and of an alloy of copper and zinc. So we're going to explore these and we're going to explain why is it that the alloy of copper and zinc is harder than pure copper. So if we're looking at this, we can see that pure copper have these in regular lattices. So they're in regular rows, which means therefore that if I apply pressure here, this row will simply slide over. And that's easy for it to be done. But if we're looking at alloy, which have both zinc and copper, we can notice that the size of these atoms, they are completely different. And because they're different, that regular row that pure metals are used to, it is no longer there. We classify this as a bit of distortion. It's now out of shape, which means they're not going to be sliding as easily as it would have been if it was pure copper or pure metal. This question, it can be given to you with any metal whatsoever. So they can give you pure copper, they could give you pure iron, right? The concept remains the same. If it's pure, it's in regular rows, so it can slide easily. That makes it a bit softer. But if it's an alloy, the shape is distorted due to the difference in size of those particles, of those atoms, and it means that the layers cannot slide easily. So that's our answer for this. Okay, atoms are of different sizes. Layers are distorted. So layers cannot easily slide. And that's the full extent of this response. As we move along, we're looking at the alloy, just the same, that same alloy of copper and zinc. So we have a 5.25 gram of a sample of that alloy, and it contains 13% of zinc by mass. We're going to try and find the mass of copper that is in that initial sample that we have. And we're going to represent that information in 3 significant figures. So the first thing we need to know is that percentage is represented in 100. So if this alloy, the alloy contains zinc and it also contains copper, and zinc makes up 13.5%, it means that copper is going to be making up the remaining of that 100%. So to find that for copper, it is going to be 100 minus that 13.5, and that's going to give us a percentage of 86.5. So that's the percentage of our copper. So all we need to do now is find 86.5% of that total sample mass. So that's 86.5 divided by 100, because our percentage is out of 100. And then we're going to multiply by that 5.25 grams. And that should give you an answer of 4.54125 grams. But it says we're going to give the answer to 3 significant figures. That's what it says. So in order for us to represent it to 3 significant figures, we're going to have that cut off right here. And the number that comes after is 1, which means we can just write that as is. So our answer is 4.54 grams. That is our answer represented to 3 significant figures. Now, question 2. A student prepared copper sulfate by reacting an acid with excess copper carbonate, and figure 3 shows the first 2 stages of the preparation for copper sulfate. So let's explore the stages. So the first stage, we can see that we have our beaker, we have our acid, and our copper carbonate is being added. And remember, this is in excess, which means we're going to be adding more than we actually need. And then for stage 2, we can see that unreacted copper carbonate because it is in excess. And we are filtering, that's filtration, so that we can remove the unreacted from the copper sulfate solution. Now, the first question says, what is the formula of the acid used to prepare copper sulfate? And this is our salt. This is our salt. And for all salts, the acid's name is usually from the very last part of it. So we're looking at that sulfate, and we're going to decide which acid will actually give us this. Now, just to think about it, sulfate, you should be thinking about sulfur. And sulfur have a symbol S. And that 8 portion suggests that oxygen is present. Suggests that oxygen is present in that compound. Now, let's look at these. This is HCl. We're not seeing any sulfur in this. We're not seeing sulfur in this either, which means that this must be the one that is our response. So this is your hydrochloric acid, and all salts formed from hydrochloric acid ends with chlorides. For their nitric acid or nitric acid, however you pronounce it, all salts will end in nitrate. So our only option for this is sulfate. So that's our sulfuric acid. As we progress to 2.2, why is excess copper carbonate added or used in stage 1? What's the purpose of using it? And this is because we want all the acid to be fully used up. So all acid is fully used up, and that's the purpose of adding it in excess. Now in beaker N, it contains that copper sulfate solution. We're going to describe how the student would produce copper sulfate crystals. And by crystals, we're simply thinking about those solids. And if you remember this required practical, you usually use an evaporating dish, and the crystals are usually formed at the bottom of it when you leave it over time. So all we're going to do for this, we're going to heat it gently. We're going to heat solution gently. Then leave to cool. That's the extent of what we will do for this. As I mentioned, this is a required practical, And these are usually how the questions are structured for this required practical. So you either get it in detail to answer these questions, or it might be a 6 marker for you to write the method. So if we go back up, you can use this diagram to help you to remember the method for this. So you add in your acid to a beaker, then you add your carbonate or your oxide in excess. Once it's in excess, you filter to remove that excess, right? Then you heat your filtrate, which is your copper sulfate in this case, gently, and then you leave it to cool. So this is essentially a 6 mark question that you could have gotten. Now, a student investigated the thermal decomposition of copper carbonate, and thermal decomposition, remember thermal means heat. So we're just using heat to break down a compound. So use of heat, break down a compound. And in this case, we're going to be breaking down copper carbonate. So 2 products are going to be formed as a result of this decomposition. It's given us the setup of what will happen. So we can see the heat, which is used for thermal decomposition. And we're going to be heating 1.2 gram of that copper carbonate. So the method that was used, so we add 1.2 gram of copper carbonate to the test tube. We're going to heat the test tube and content until the mass does not change. And then we're going to record the mass of the contents of the test tube after heating, and they're going to repeat steps 1 to 3 with different masses of that copper carbonate. This is the results table, and the first thing it's asked us to do is to plot a graph and draw a line of best fit. So we can see based on the table, we have the mass of the copper carbonate in the test tube before heating, and this is the mass of the contents of the test tube after heating. So these are some key things that you're going to be looking at when you're actually plotting your graph, because you don't want to confuse these axes, because it's quite easy for you to mess up these numbers. So I've went ahead and I've pre-planned or pre-plotted the graph. Okay, and notice this axis, your y-axis, is after content. So if I'm doing this, I would usually right there where my information would go, so I'm not confusing them. So I have it noted down already which axis each of these information will be. So when I'm plotting that graph, I'm not getting confused as to which data goes where. I am not getting them muddled up. So this is it plotted, and I've drawn my line of best fit. I did this freehand. Yours should look a bit nicer than mine since you'll have your ruler to use. So this is what it would look like once we have drawn our line of best fit. Our points are plotted correctly. That will give you 2 marks. And then 1 mark is for that line of best fit. So very nice graph question, this one. Now let's carry on to 2.5. Now, why does the mass of the contents of this test tube decrease in mass when copper carbonate is thermally decomposed? There's something I want to draw your attention to. We are heating a carbonate. And because we're heating a carbonate, it means that a gas is going to be formed. And yes, you think it, CO2. All carbonates, if you decompose it or you react it, it will always produce carbon dioxide. So that carbon dioxide, remember, we were using a test tube. That's my heat. We're using a test tube that was open, which means, therefore, that the carbon dioxide gas would be escaping. And because it's escaping from the container, we are unable to account for that mass, which is why it appears as though the mass have decreased when really it haven't. Okay, so we can just mention the gas escapes the test tube. Or if you want to say CO2 escapes, you really know the name of the gas, right? CO2 escapes, that's absolutely fine as well. Now for question number 3, and question number 3, this is a 6-marker question, and it's asking you to compare 2 different structures. And this is a leveled response, which means in order for you to get to that higher level, band of marks, that 5, 6 marks, that level 3, thereabout, then it means therefore, not level 3, level 2, because this is just 2 levels that this one is separated into. So to get that 4, 5, 6, then it means you would have to make mention to similarities in bonding and structure and differences in bonding and structure for you to maybe attain that mark. So that compare similarities and differences. We're going to explore this in a bit of detail. I'm going to write it on this side over here so I have enough space. Okay, so let's start with our similarities. Remember, it says we're comparing structure and bonding for each of these. So it means, therefore, that my similarity must contain some information about structure, some information about bonding. My differences must include information about structure and bonding as well, in order for me to maximize my opportunity of getting that higher level of mark. Okay, so similarities, so both have strong bonds. Yes, I know that the type of bond that they have is different, but both bonds are actually strong. So yes, this is ionic bonding, and the oxygen is covalent in nature. So technically the type of bonding is different, but the bonds themselves, those are quite strong. So that's a similarity in terms of bonding. And in terms of structure, each of them have full outer shell, because that's the aim of bonding, for these atoms to have a full outer shell. So it's still a thing. So we can mention that particles have full outer shells, right? And that's our those are our similarities, one representing structure, the other representing bonding. Now let's look at our differences. And for differences, in a compare question such as this, I usually do this in a table format because it helps me to track the information to ensure that I have it all. So I'm going to do this in a table. Let me just quickly draw my table up. So this side is going to be for my sodium chloride. And this side for my oxygen. And I'm going to start comparing them. Okay. So first thing I'm going to mention, based on this, I'm taking it back to key stage 3, right? So we know that sodium chloride is a compound made of 2 different atoms, chemically joined or bonded. Then I can mention for my oxygen, oxygen is an element made of atoms of the same kind. And I will also mention that O2 is diatomic. All right, I can mention that. Now let's carry on. That's one of my difference. One difference. Now another difference, I can mention that sodium chloride is a giant ionic compound. And for my oxygen, I can mention that O2 is a simple covalent. Oh, well, let me just go back up. Covalent molecule. So I have that as my structure again. So those are all structures. Okay, so let's go into the bonding realm. So these two up here, let me just note that down. So these two here, that's colorful. Those two, these refer to structures. Right, those are comparing the structures. Now we're going to look in the bonding realm now. So NaCl has ionic bonds with oppositely charged ions, while my O2 has covalent bonds with, that should be with my eraser, with electrons being shared. I can add this, electrons are transferred from Na to Cl. That's a difference. Now let's explore the magnitude. I can mention that NaCl has electrostatic force of attraction between ions, while for my oxygen, O2 has intermolecular force between molecules. And I'm going to just include weak here and strong here. Let me just highlight those so you can see it clearly. All right, so I'm just going to include those. So at least we can mention the magnitude of these forces. So the electrostatic force of attraction, yes, that's strong, but the O2 that have weak intermolecular forces between the oxygen molecules, that makes it that a bit weaker than your ionic compound. Now, this is essentially able to give you that full 6 marks. So that's full 6 marks for that one. Let me just quickly note this down so you can refer to this as the bonding portion of it. So that's your bonding. In terms of your similarities, we have this representing your bonding, this representing your structure. So as you can see, we have similarities and differences for both structure and bonding within your sodium, chloride, and oxygen. Okay, so that's your 6 marks. Not so bad. Now for number 4, carrying on quite nicely. Number 4, we have nitric acid, which is a strong acid. What is meant by the term strong acid? So if you remember your strong acid, such as your nitric acid, it ionizes completely in aqueous solution. So what I mean by ionize completely is if I have HNO3 and I put it in aqueous solution, it is going to form your H plus and your NO3 minus. Notice that H plus have completely dissociated from that NO3 minus, and that's what we mean by complete dissociation, right? So it's going to be completely ionizes in aqueous solution. Got aqueous wrong. In aqueous solution. Now, on the flip side, because we're doing this, let's just finish off. On the flip side, if we have, let's say, a weak acid, so if we have a weak acid, like your CH3, like your ethanoic acid, that partially ionizes. And what that means is we're going to have this CH3, COO minus, plus your H plus. So we can see that we still have some hydrogen remaining in our ethanoate ion. And because we still have some hydrogen remaining there, it means that it's partially dissociates. Only some of the hydrogen was given off. The rest remain within the massive chunk of that, the other ion. Okay, so this was dissociate, the other was not, partial. Okay. Now for 4.2, nitric acid is used as a dilute aqueous solution. What is meant by dilute? Let's look at the term dilute. If something is dilute, it means that it has more water than it does nitric acid. And that's what it is. It means that it has low concentration of nitric acid dissolved in water. That's what dilute means. Now 4.3, so we have 10 centimeters cubed of nitric acid solution, and it has a pH of 1. Water is added to that nitric acid or nitric acid solution to change the pH of that nitric acid solution to pH 3. How does the hydrogen ion concentration change? Now let's just draw a snippet of my pH scale. So that's 1, 2, 3. That's all we need. So we have nitric acid being in this realm here, and it mentions that we've added water and the water moved it from 1 to 3. So this is the direction it's going. Each of these jump will adjust the concentration of H plus by a factor of 10. Now notice that this going this direction have a high concentration of H plus. So which means going in the opposite direction, we're decreasing that concentration. So we're going to decrease by a factor of 10 times 10, which is 100. So we're going to decrease by a factor of 100 in that case, because we're going to be from pH 1 to pH 3, which is less concentrated in terms of its hydrogen ion in terms of its H plus concentration. Was losing my words there. Now for 4.4, write the ionic equation for the reaction between an acid and an alkali. So we know the acid and an alkali, once they are reacting, it's called neutralization. Reaction. And this is where we form a pH of 7. So we have from our acid, we have our H plus. From our alkali, we have our OH minus. And if we look at these ions, you'll notice that both of these will form your H2O. And that is your ionic equation for the reaction between acid and alkali. And this will always be your ionic equation once you're doing neutralization reaction. It's always forming that 1 mole of water. That's the aim of neutralization. So this equation shows the reaction between magnesium carbonate and nitric acid. What is the ratio of the number of moles of magnesium carbonate? So let me just put that under. To the number of moles of nitric acid. Now, just looking at this, you will see that it is a 1 to 2 mole ratio. So that's 1 to 2 mole ratio. 4.6, a student mixed some magnesium carbonate with excess nitric acid. The student then dropped 2 drops of universal indicator into the solution. What color was the solution after the addition of the universal indicator? Let's just do this as basic diagrams, really, right? So this is my sodium carbonate, and I'm just going to draw it as a level like that, just to prove a point. Okay? And we have nitric acid, which is excess, and by excess, it means that we have added more than we need. So let's say this is my nitric acid and I'm adding it in excess. So which means that this balances off my magnesium carbonate, and I'm adding excess, which is a bit more than that. So if this is the amount that I need, and I added whatever is above this line is excess, it means therefore that when I add that universal indicator, this excess will be detected. And because this is my nitric acid, and acids are red on my universal indicator. Remember, green indicates neutral, which is a pH of 7. And blue indicates alkaline, which is the pH range of 8 to 14, right? So as it gets to 14, it becomes a bit more purple as opposed to blue, but this is the range for your alkaline. The student investigated the temperature change when different masses of magnesium carbonate were reacted with excess nitric acid. It gave us a setup, and this is a temperature change, which means from looking at this, it's testing some exothermic, endothermic reaction. This is typically a required practical where you're using your polystyrene cup to conserve on heat to ensure that it's insulated. So we have our magnesium carbonate being added to our nitric acid. It's in a polystyrene cup because of insulation. We don't want a lot of heat to be transferred to the surrounding. And we're using thermometer, obviously, to check the temperature as it changes. So the method that we have, so we're going to pour that 50 centimeters cube in the polystyrene cup, measure the temperature of that solution. Then we're going to add that mass of our magnesium carbonate, stir the mixture, measure the temperature, and we're going to repeat steps 1 to 5 with different masses of our magnesium carbonate. Now 4.7 said give 2 improvements to the method to produce more accurate results. Do not, and I'm going to emphasize this, do not refer to improvement to the apparatus in your answer. So if you do something like this, saying that you need a lid, that's wrong, because it says do not make any reference to improvements to the apparatus. We're just looking at the method. So that's this method. We're looking at it and we're seeing how best we can improve it, right? Now let's quickly look at this. So pour 50 centimeters cube in our polystyrene cup. Yes, that's accurate. We're going to measure the temperature of the solution, which we ought to do since it's temperature change. Then we're going to add 0.50 grams of magnesium carbonate, stir the mixture, and we're going to measure the temperature. What temperature are we going to measure? Is it any random temperature? No. In this case, we're going to want to measure the highest temperature. So that could be an improvement. Measure the highest temperature. Because remember, once we've added that magnesium carbonate, the temperature is going to start rising. But we don't just want to say, okay, it rose by 1, let's record that while it's continuing to rise. We want to measure that highest temperature. So the temperature it hits and it's not moving any further, that's the temperature we want. We're going to repeat step 1 to 5 with different masses of magnesium carbonate. Yes, we can do that, but we can also include a 7th step. And that's where more accurate results come in. So whenever it asks about more accurate results, always think, repeat, and calculate mean. So this is an additional step that you could do to improve your results. Repeat, calculate mean. That's something that we can do. So whenever a question asks, what can we do to get more accurate results? If the scenario does not include anything about repeating or calculating mean, then that's one of your best bets. Number 5, we have nitrogen reacts with hydrogen to produce ammonia. And we're going to complete the dot and cross diagram for the ammonia molecule that is produced when we have that reaction taking place. Now, first, let's look at where our hydrogen and nitrogen are. So we have nitrogen is over here in group 5, which means it has 5 electrons in outer shell. And because it has 5 electrons in its outer shell, in order to be stable, it needs to have a full shell. And a full shell for this, since it's in the second period, means that it has 2 shells. So the second shell can hold a maximum of 8. And it already has 5, which means it needs 3 more. Needs 3 more electrons. So this we know, in order for it to be stable. Now let's look at hydrogen. Hydrogen is not a member of a group, but we know that it only has 1 electron, and it's in period 1, which means it only has 1 shell, and the first shell can only have 2 electrons, but hydrogen only have 1. So which means our hydrogen, it needs 1 more electron to have a full outer shell and to be stable. Now let's look at how we can merge this information so that we can complete this dot and cross diagram here. Because nitrogen, it needs 3 more electrons, we know that it's going to have 3 pairs of electrons. So nitrogen, it needs 3 electrons, so it's going to have 3 pairs of electrons. So we have 3 overlaps, so it means that 1 electron from nitrogen will be in each, and this is 3, 4, 5. So those are from your nitrogen. So your hydrogen, it needs 1 electron to be stable. So it means therefore that hydrogen will only have 1 overlap, and that 1 electron for hydrogen will be in those overlaps. Let's check if all of these are stable now. Hydrogen, we know it has 1 in there, and it needs 1 more to be stable. So that's that X there. This as well has 1 electron, it needs 1 more to be stable. Has 1 electron, needs 1 more to be stable. So all our hydrogen are correct. Now let's check our nitrogen. Nitrogen needs 3 more electrons to be stable. So it needs 3 pairs of electrons. So that's 1, 2, 3. 1 of its electron in each. And then we have these 2 that are unbonded. So if we check, we should have 8 electrons. That's 1, 2, 3, 4, 5, 6, 7, 8. So now nitrogen is all done as well. And this is the structure for the bonding between nitrogen and hydrogen to form ammonia. Hope that helped you to figure out how to do this. Use your periodic table. It really works when you're actually doing something like this. Now 5.2, we have this equation. And for this equation to produce ammonia, we're basically doing a follow-up of this, a calculation bit. Calculate the mass of hydrogen that is needed to produce 25 grams of ammonia. Now, this is a classic example of reacting masses. And for questions like this, I always highlight the species that I'm concerned with, because even though you got an equation, you will usually be concerned with only 2 out of the bits that you got in the equation. So it asked me to calculate the mass of hydrogen. So I know that I'm concerned with hydrogen. And it also asked me to, it gave me information, about ammonia, 25 grams of ammonia. So I know I'm going to be concerned with ammonia as well. So those are the only 2 species that I'm going to be concerned with. I'm not even going to look at nitrogen because I don't need it for this question. So we're going to calculate. I'm going to write it here. So that's 3H2, so 2 NH3, because those are the only thing that I'm concerned with. First thing I'm going to do now, I'm going to put the information that I've got. Let me change the color of my ink. So this is 25 grams of ammonia. So in order for me to find what hydrogen is, the first thing I'm going to do is I'm going to convert that 25 grams into moles by dividing by the MR for your ammonia. And that MR for ammonia is going to be 17. Remember how I got that? Let me just do it here. So you remember how I got that 17. So that's 14 plus 3, which is 17. So once I've done that, I'm going to get a number of mole of 1.47 moles. And this is going to represent that 2 moles of ammonia. Remember, it's in a mole ratio of 2 to 3. So if this represents 2 moles, I need to now figure out what 3 moles will be. And I'm going to be using that mole ratio to help me. So in order for me to do that, so moles is equal to that 1.47, which represent the 2, multiplied by 3/2, so that I can find what 3 mole actually is. And that's going to give me 2.205 moles of my hydrogen. And then I can work out the mass of hydrogen that is required by converting from moles to mass. So let me just work that out. So mass of H2, that's going to be my 2.205 multiplied by 2, and that's going to give me 4.41 grams. And that is going to be my answer, 4.41. Figure 7 shows the displayed formula equation for the reaction between hydrogen and nitrogen, and we can see what figure 7 looks like. We're going to explore this in a second. Now, in the reaction, the energy released forming new bonds is 93 kilojoules per mole greater, and that's key thing, greater than the energy needed to break the existing bond. So because we know that the energy released is greater, we know that this reaction is exothermic. Just write that here. So the enthalpy change is going to be negative 93 kilojoules per mole. So let's explore calculating the H single bond H bond energy from the data that we have been given. So I usually separate this in terms of bonds broken and bonds made. So I'm just going to write it down on this side. I'm going to do the calculation over here. So bonds broken and bonds made. That's how I usually do it. So let me just highlight all the information that I have before I start to do anything else with regards to my numbers. I can see that I have 1 of this bond. Can't see any more N triple bond N anywhere. Okay, let's look. I can see 3 of those bonds. So that's H single bond H. And let me see, there's 1 more bond remaining. And that's 2, 3, 4, 5, 6. So 6 of those bonds. So I have 6 of those bonds, 3 of these, and 1 of the N triple bond N. So I have noted down all the bonds that I have. Now I'm going to start doing my calculations. So for my bonds broken, I know I'm going to break 1 of my N triple bond N. So that is going to be 945 plus my 3 times, well, I can just leave that as 3x because I do not know what that bond is. So that's going to be my 3x. And for my bonds broken, my bonds made, sorry, that's going to be 6 times my 391, which is going to be 2,346. So that's going to be my answer for this one. So in order for me to find my energy released, that's going to be equal to my bonds broken minus my bonds made. And that's why I set this out as is. So I always remember that it's BB minus BM. So I will always remember it like that. So when it comes down to me doing this calculation, I already have it. So now remember, our energy released, it was given to us already to be negative 93, because that's energy released. So I'm just going to note that down as my energy release, negative 93, and that's going to be equal to my 945 plus 3x, put that in a bracket, minus my 2346. And then I can just rearrange this equation just to ensure that I have x on one side. So my 3x is equal to negative 93 minus 945 plus 2346. And that's going to give me an answer of 1308. Divide both sides by 3. So x is going to be 436, and that's going to be my bond energy for breaking 1 mole of my H, single bond H. That's my answer. Just highlight this so you separate from everything else. So that's my answer there. For question 5.4, it's regarding the fact that energy is released during the production of ammonia, and it shows us figure 8, which is just a part of the reaction profile diagram for this, and we're asked to complete some particular things. We're going to complete the profile line, we're going to label the energy levels for the reactants and the products, and we're also going to label the overall energy changes. So it mentions that energy is released, so initially you should be thinking exothermic. And we know that when energy is released, it means that we're going to begin with a reactant, because every reaction begins with a reactant. So these are my reactants: nitrogen and hydrogen. So these are my reactants. And once those reactants have that activation energy and they begin to react, then it means therefore that they're going to be releasing some energy. And if something releases energy, what's left, which are the products, it will now have less energy than it had before. So this line would represent my ammonia, which have less energy than my reactants. And then I'm just going to pump and connect. Okay. Now it did not ask us for activation energy, so we're not going to focus on activation energy, but what we're going to focus on is the overall energy change. And for that energy change, or energy started with what our reactant have, and then we release some, and that change allowed us to end up down here. So my change is from my reactant to my product, and this would represent my energy change. So let's just double check to ensure that we have all of this all completed. So complete our reaction profile diagram. I can see that it's completed. Then the next step is to label the energy level of our reactants and our products. We have our reactants there. We have our product there. So that's completely done. And then the last one is for us to label the overall energy change. And we can see that the overall energy change, we started at our reactant, and that change allowed it to drop, okay? And then it's pointed towards our product. So we have completely done all of this, and that's our energy profile diagram for the reaction that produces ammonia. Question 6, in the earth, most metals are found as compound. We're going to name one metal that is found in the earth as metal itself. So you could go for any of the common metals that is below hydrogen in that reactivity series. So your gold, your silver, your platinum. You can go for copper as well, but that's not one that I would go for personally, but that is something that you could go for as well. It is allowed in the mark scheme. If you want to go for copper, then that's absolutely fine. It's my last go-to for this thing, but yeah, it is actually acceptable. So here's the part of the reactivity series. So we have the most reactive at the top as usual, and as we move down, it gets gets least reactive or less reactive. We're going to suggest the most economic method that we can use to extract metal Z from a compound that contains that metal. Okay, so if you remember, metals that are above carbon, let me just highlight that carbon, metals that are above carbon, it is usually extracted by electrolysis. And electrolysis, it costs money because it uses electricity, a lot of it, in order for extraction to take place. So the most economic method that we can use for this is reduction by carbon. Because we can do this extraction, because remember, more reactive element, it can displace a less reactive element from its compound. So if we have this in a compound, metal Z, and we react it with carbon, carbon is reactive enough to displace it, so we can get that pure metal, and it's cheaper, so it's more economical. Now, the next bit is we're given this electrolytic cell, and it's based on the extraction of aluminium from aluminium oxide. And we have our positive and negative electrodes. They're set up as it normally is. Remember, for extraction of aluminum, it's not usually set up as the normal electrolytic cell that you're used to, that looks like this. It's more tend to go towards this method where we have our anodes over the top and our cathode lining right the bottom and the sides of the container. We're going to name substance X. So we have a molten mixture of aluminum oxide and substance X. What is this substance X? So you should be thinking it cryolite. And that cryolite that is used to reduce the melting point of that aluminum oxide, so it takes less energy to melt it. So just note that down. Used to reduce the melting point of aluminum oxide. That's the purpose of our cryolite. Okay, let's carry on. Question 6.4 looks at us explaining what happens to a positive carbon electrode during the extraction of aluminum oxide. So for this, let's first write the formula for aluminum oxide. So Al2O3. Now this is going to be molten. This is going to be molten, which means that only two key ions will be in there, and those are your Al3+ ion as well as your O2- ions. Each of these will be attracted to either the anode or the cathode. Now, obviously, opposites attract. So my anode is positive, so it's going to attract my anion, which is my O2-. So in order for when that happens, let me just write the equation. So at my anode, I'm going to have my 2O2- forming my O2 gas plus 4 electrons. If you write it like this as well, it is completely acceptable if you write it like this as well. And to be honest, I usually encourage my students to write it like this if they're a bit confused. So it will suggest that if it's a negative ion, you minus the electron to form the atom. If you remember it like that, absolutely fine. Okay, so this is what's going to happen at the anode. So my anion, oxide ion, is going to be attracted to the positive anode. And once that happens, it's going to lose 4 electrons and it's going to form oxygen gas. But another reaction is going to take place there. And that's where your O2 gas is going to be reacting with your carbon. Because remember, each of these are made of carbon. So it's going to react with that carbon to form carbon dioxide, which means that electrode is going to be depleted and you're going to have to be replacing it continually. So to answer this question, oxygen is produced, which reacts with the carbon electrode producing CO2. So the electrode has to be continually replaced. And that's what's happening to the carbon electrodes that are at the positive end of this electrolytic cell. Okay, and this is a reaction that is taking place as a result of that happening. So that's at your anode. Now the next question, it says the formula of aluminum oxide is as such. We've written that already. Write the half equation for the reaction that's taking place at the negative electrode. And again, opposites attract. So we know that at the negative electrode, which is your cathode, that will be your aluminum ion. So in order for us to write that, so it's your aluminum Al3+, and that's going to form your aluminum metal, but we're going to need some electron. So as I would mention to my students, if it's a positive charge, you add the electron on the same side where it is. So it's +3. So we're going to add back those 3 electrons to form that aluminum. Okay, so that's what's going to happen in that scenario. Let's carry on. Now for number 7 is about the halogens in group 7 of the periodic table. And we're going to explore the what happens in terms of them bonding with other things, as well as reactivity of these metals. Okay, so let's look at number 1. So calcium reacts with chlorine to produce calcium chloride. Explain what happens to the calcium atom and to the chlorine atom when this reaction is taking place in order for us to form that calcium chloride, sorry. Now, first, let's look at the groups that they're in. So we are looking at calcium, this is calcium, and we're looking at chlorine as well. So this is in group 7, and this is in group 2. So some key information. So this is a metal, which means it's going to lose electron. And it's in group 2, which means it has 2 electrons on the outer shell, so it's going to be losing 2 electrons. So this is lose 2 electron, and it's going to form a 2+ charged ion. And for our chlorine, which is in group 7, it can have a max of 8, and we know that nonmetals gain electrons, and it's in group 7, can have a max of 8, so it means that it's gonna gain 1 electron, and it's gonna form 1- ion. So that we know. Okay, so we're gonna note that down in over here, that each calcium, just write the symbol, atom loses 2 electrons. And we know that each chlorine atom gains 1 electron. Now the follow-up for this is for us to state the ratio at which this will react. Okay, so 1 calcium atom will react with 2 chlorine atoms to form Ca2+ and Cl- ions. Okay, and that's the full picture. So once you're looking at a question like this, formation of ions in order for compounds to be produced, right, you can use your periodic table to help you. It is there for that purpose. So use it wisely so that you can maximize your marks for these. The next one, it uses the periodic table quite nicely as well, and it's for us to explain why chlorine is more reactive than bromine. And this is where we're going to look at the position of where these are. So based on what we have said earlier for this bit of information, nonmetals, hold on, let me just go back up a bit. So nonmetals, they gain electron. That's a key information, and all of this is what we're concerned with, those group 7 elements. And if they're going to be gaining electron, it means therefore that it needs to be smaller. It needs to have a smaller atomic radius. Let's just draw what the radius would look like, the atom would look like for each of these. So if we have fluorine, fluorine is in period 2, so it has 2 shells. Then chlorine in period 3, so 3 shells. Then we're going to have 4 shells. That 4, 1, 2, 3, 4. And as we're moving down, we're going to have an additional shell as we're moving down that group. So for your nonmetals, remember the key thing that happens is the fact that they need to be able to gain electron. So this is going to represent your chlorine, and this represents your bromine. So we can see chlorine, it has fewer electron shells. So we're going to write that. So Cl has fewer electron shells. We can also see that outer shell for chlorine, it is closer to the nucleus. So we are going to mention that, fewer electron shells. So electrons, let me just say outer, electrons are closer to the nucleus. And if it's closer to the nucleus, it means that it's going to have a stronger nuclear attraction, right? Therefore, has stronger nuclear attraction. And because of that stronger nuclear attraction, that leads us to the last point. So it's going to gain electron more easily. So we'll gain electron more easily. Or easily. Can we say more easily? Right, so it will gain it easily. More, yeah, we need to say the more there because it's comparative. Right, so it will gain it more easily than your bromine. And this is the full picture as to what will give you those 4 marks. So electron shells, outer electron shells, are closer to the nucleus, therefore has stronger nuclear attraction and will gain electrons more easily than that of your bromine. Question 7.3 shows us a table of the boiling point for 4 hydrogen halides, and it's asking us to describe how the boiling point of the hydrogen halide changes as the relative formula masses changes. Now, this is a describe question, so it means that we're not going to tell why it's happening. We don't need to tell why it's happening. We just need to look at that general trend. So if we're exploring these, we can see that as we move down this group here, we can see that the relative formula mass increases, because if you look at the masses on the periodic table, you'll notice that even though hydrogen is 1 for all of them, the masses of your fluorine, chlorine, bromine, and iodine actually increases as you're moving down. So which means as we go down, relative formula mass, so that's your MR, it increases. Now let's look at what happens to the trend in boiling point. So the boiling point trend, we can see the general trend is the fact that it increases as well, right? So it increases as well, with an exception of fluorine, which does not conform to that trend. So if we're going to describe what is happening, so as the relative formula mass increases, the boiling point also increases, except for hydrogen fluoride. Except for hydrogen fluoride, which does not follow this trend. Right? And that's your 2 marks. You're just describing what is happening. You do not need to give a reason for it happening. But if you want to give a reason for that happening. It's due to the intermolecular force that exists between them. You look a bit further at intermolecular force if you end up doing A-level chemistry, but in the meantime, you just need to remember that the official trend is that the boiling point increases as we're moving down that group, especially in hydrogen halides, except for hydrogen fluoride, which have a different type of intermolecular force, which is basically stronger than the others. Okay. Now for question 8, which is our last question, carbon nanotube are cylindrical fullerenes, and it's represented by this structure. We're going to describe the arrangement of carbon atoms in the carbon nanotube based on the figure that we have right there. Okay, so if we're looking at these, let's just pick any of these. So the arrangement, so this, just looking at it, you can see that it have some hexagonal rings, or if you want to say ring of carbon, that is absolutely fine, right? So hexagonal rings. If you want to put of carbon, that's fine, but you must have this bit, hexagonal, because that's the key thing that describes the arrangement of those carbon atoms within that carbon nanotube. So this nanotube is usually used in electronics because of those delocalized electron. Give one other use of this happening. So it is used in nanotechnology. So we can just write that down. Nanotechnology. It is also used in some body armor or sporting equipment. So you can use that as well, right? So sporting equipment. And another key use is drug delivery. And you would have explored drug delivery because it's hollow. Drugs can be placed on the inside so that it can be delivered to a site that is needed. So that's another key use of nanotubes. Okay. Now for 8.3, we have a nanotube that contains 2,380 carbon atoms. And we're going to calculate the number of moles of carbon in this carbon nanotube. And we're going to use a particular equation. So number of moles is equal to the number of atoms divided by the Avogadro's number. So essentially all we're doing here is just dividing 2,380 by our Avogadro's number, 6.02 times 10 to the 23rd, because each atom contains this number of particles, and this particle is just 1 mole. So now we can use this to figure out how many moles of it we actually have in that 2,380 atoms of that carbon, and that's going to give you an answer of 3.95 times 10 to the negative 21, and that is going to be the number of moles that we have. So that's our answer for that one. 8.3, so we're going to explain why the carbon nanotubes can be used in electricity, to conduct electricity. And whenever you're thinking about something conducting electricity, let me just highlight this and note it on the other side. Whenever you are thinking about this, you're thinking about 2 concepts. Let me just note it over here. And those 2 concepts is either delocalized electrons, or free ions. These are the only 2 cases where things will actually conduct electricity. So when you think of delocalized electrons, you're thinking about these things, metals, and you're also thinking about graphite, fullerenes. And when you're thinking about free ions, you're thinking about compounds, ionic compounds in its aqueous or liquid state. So that's what you're thinking about when you're thinking about something conducting electricity. So in this case, we are thinking about it in terms of delocalized electrons, but for fullerenes. So we're going to write about this now. So each carbon is bonded to 3 others by covalent bonding. And because it's bonded to 3 others, it means therefore that one electron is free, is delocalized. So we have one delocalized electron per atom, which means these delocalized electrons, they can move through the structure and carry that electrical charge, right? So delocalized electron can carry charge through the structure. Good luck on your exam, and like and subscribe so that I can make more videos like this. And please tell me in the comment section if there's anything that you would want me to go through, or if anything that you would want me to address, any past paper that you would want me to go through. As long as I have not been through it already, then by all means, pop it into the comment section so that I can get on it.